Okay, so today I would like to talk about the stateMonad. This is the simplest stateMonad ever. There's nothing simpler found. And let me first define the problem. So our problem is a function which is taking one argument on which we are going to modify. No, transform, maybe it is better word. But meantime, we are adding here some side effect. Yeah, side effect. And finally, we of course are doing some operation on our argument. And actually, this is the main flaw. Is that this is exactly that what we are expecting from this function. So this is that operation. This function is fully correct. Yes, in many times we just replace print line with some logger or log and log anything important or something important for us. But from the functional point of view, it is not fine because there is a paradigm about the referential transparency. Means that whenever I call my function with some argument, I can replace all these executions by the result, and side effects are something which are breaching this paradigm. Yeah, and other thing is that actually in functional programming you do not have side effects. In side effects which are related, which are relying on the change in the internal state, because actually we are using actually immutable states. So our function looks like this. Yeah, so I have foo. So first will be my argument, second is my state. This time maybe it would be better to use a string. And now to have an access to my modified state, instead of returning only my argument, my main argument, I will return also the state. Yeah. So in my case it is like I plus 1, and here we have some s plus, and this is my part of state. Yeah, so let's call it like foo. Yeah. Then third thing is that we are not working with binary functions or n-ary functions. We are working mainly with unary functions, and actually any n-ary function we can turn into unary function, which is returning another function, of course, besides the nullary function. So in Scala we can get it with carried function, which is defined on the function. This signature is pretty important because it is something which suggests me how to turn the single value into my function, which is getting as a first argument a state and giving me back a pair of value and a state. Yeah, so for example, I would like to start my computation with single value, so I need some function, yes, to lift this value, to my function, and actually, yes, this will produce me stateMonad. Yeah, so the stateMonad is the function which is getting as an argument the state and giving me back a pair of value and the state. So first I have here an A of type A, and that we want to get is this S into A and S, and this is equal, no surprise, okay, here on A and S. So Now, the short explanation why I claim that this is a monadic function. Maybe this is a better word because it itself is not a monad. The monad, it will come when I will define the appropriate functions, yes, or type class with functions, map and flat map. So when we look at the signature, yeah, like this, we remember that this is actually and we remember that actually, let's say the monad or the monad, yes, we can express like something like that, yes, m of a. So in our case, the type of state is, we can treat it as a stable state, yes. Why we can treat it? Because from the computation point of view, so I'm interested only in this type A. So if I'm interested, and what I would like to get here, I would like to first let me first define the map function. Yes, from our m of a will be actually f of a, and this map function will get, of course, that what map function used to use. Yes, so this is function a into b. Yes, so now what I really want to do is, here, yes, in this place I have a function which is applied on I. So I will define this function outside my function foo, and then I combine my single value with a function which is doing that operation. Yeah. So how this map looks like, I have three types, S, A, and B, and first argument is no surprise, is my functor or monadic type, yes, and the second is a function which gets a and give me back b, and I am expecting to get bs. Yeah. The body is pretty obvious because actually I get a state, yeah, and then first let me apply the state to my SA. Yeah, it gives me a tuple of new value and new state. So here apply S. This S is coming from here. Yeah. The second thing is that I'm writing down what I'm returning. So I'm now applying on I am applying A on F, and I rewrite the state. Yeah, so this is my map function. So now I can replace, say, this function with my foo function with something like that. Map lift 11. Yeah, this is a little this is too little written here because I have to declare a type as well. And with my function which is taking x of type int, let's give me back +1. Or maybe I will change also the type. So it will be like x to double plus 0.2. Yeah. Okay. And just to see if it is working, so I will call it with something like, let's call it foo. Yeah. So this is what exactly I got. I will leave for you the proof that this is really functor combiner. So remember that we have to write something like map of SA, and f function, g function has to be equal to map of SA, and I have here an f combine f and then g. Yeah, you can check it if this is possible. Yeah, if this is equal. So now I would like to go to the another playmaker, so our fmap. As we remember, fmap is the something which is operate on monad of a and is also operating with function which is getting this a, so internal type or inner type of monad, and is using this inner type to produce type b, but not changing the monad. Yes. So in our case, when we have an s, yes, a and s, so our a is exactly this a. Yeah. So how we can define it? It will this like the fmap. Again, we have here 3 arguments, type arguments, and now I have 2 arguments, sa of s into a s and function, but this time I will get an a and return s, which return bs, and overall I should get bs. Yeah. And now again I need here a state. Yeah. And first, of course, I apply my state to produce or to get a new a and new state is sa of s. So this is exactly the same. So this step is exactly the same like in case of map. Yeah. But this time I apply on f function both arguments. So the first one is my a. Yes, so this is this guy. So I have to apply this guy. And the second one is my new state. Yeah. So I apply new state. And that's it, yes. Now let me check the first monad law. So maybe the second one or third one. So I have an fmap of fmap, yeah, which is getting here sa and function f and function g. This is exactly the same what fmap of sa. Here I will get some a, yes, and here I will have an fmap of f of a g. Okay, so this is exactly same. If I will look at this on the dot notation, yes, or infix notation, I explained some time ago how to do this with time classes and implicits. But generally, this is like fmap, declare flat map, yes, of f dot flat map of g. So I expect that this is the same word as sa dot flat map of x or a, yeah, f of a dot flat map of g. Yeah. So these two things are same. So let me first define f and g function because to not be lost in signatures. So let's say f will be, well, f as a function which is getting be like integer, and of course I will use here string. I do not have to use string. Maybe it would be a list and append to list, but this is the easiest thing and most understandable So in that case I will write, say this will be just incrementing that value, no, not incrementing by this value, it will change this value to double and increasing this value by like this, 2/10, and in f function. Yeah, there's a second function, the g function. I have to remember that this time I have here double, again string, d, let's say it was string, got value. Here is in g function. Yeah. Semicolon I'm using as just a delimiter to show where is the state, what part of state comes from the function of f and g. Yes, the text is almost the same. This is because yeah. So I have now fmap of lift 11, again, yeah, string, and now, oh, excuse me, fmap of lift, and here is a function f, function g, and yeah, so when I call there is 22 with empty string, get value c. And now let me define the right hand side. So in that place here I will have an access to my I, which is integer, yeah, and fmap of a with I and g, yeah. So now res 20 again with the same. So you can see the result is exactly the same, yes. So summary net, yes, the stateMonad is nothing else like the functions map and flat map, which are defined on function with this signature. Yes, this is our hero today, and actually there is nothing else in the simplest stateMonad ever. Thanks guys, and enjoy.